Hello, this is Elizabeth Fisher. This is my second presentation showing you how to use tables to look up thermodynamic properties. I'll be doing 3 quick examples and then I will give you 3 problems to try for yourself. In all of these problems, I specify temperature and 1 additional property. Okay, here's the first question. CO2 is at 300 Kelvin and has a quality of 0.2. The questions are, what phase is present? And what are the values of pressure and specific volume? Remember, the quality is defined for vapor-liquid mixtures, and it's defined as the mass of vapor divided by the mass of the entire mixture. Because the quality is specified and has a reasonable value between 0 and 1, we know that the CO2 is a mixture of saturated liquid and saturated vapor. To solve the rest of the problem, we will be using thermodynamic property tables similar to the ones you have in the back of your textbook. You need to find tables for the correct chemical compound, in this case CO2. There will be several CO2 tables, and we need to use a saturation table because we know we have a mixture of saturated liquid and saturated vapor. We need to find a temperature table because we know the value of temperature, and it's a nice round number. Let's go to the line of the saturation table corresponding to the specified temperature, 300 K. Because we have a vapor-liquid mixture, we know that the properties will be somewhere between the saturated vapor properties and the saturated liquid properties. Vapor properties are shown with subscript G, and liquid properties are shown with subscript F. And so we need to look at those values on the line that's highlighted in blue. We can also read CO2's pressure directly from the table. Because we have a saturated liquid and vapor mixture, the pressure is equal to the saturation pressure at the specified temperature. In other words, Psat, which is equal to 6.7131 megapascals. Now let's use the quality to find the specific volume. We need to calculate a weighted average of the saturated vapor and saturated liquid properties. The weighting factors are X for saturated vapor and 1 minus X for saturated liquid, which makes sense because X just tells you what fraction of the mixture is made up of saturated vapor. So here's the equation for V in terms of VF and VG. Let's go back to the saturated CO2 table and read off values of VF and VG, those values that are highlighted in yellow. Then we can plug in numbers and find the value of specific volume V. And we can summarize all the answers to question 1. So if we have CO2 at 300 Kelvin with a quality of 0.2, we know that it is a vapor-liquid mixture, saturated vapor and saturated liquid. Its pressure is the saturation pressure, which is 6.7131 megapascals, and its specific volume is equal to 1.92 times 10 to the minus third meters cubed per kilogram. So on to question 2. In this question, we know the temperature and the specific volume of the CO2, and we want to find what phase is present, and we want to find the value of specific internal energy. This time, we don't know for sure that we have a saturated vapor-liquid mixture, but the saturation table is still a good starting point. The relevant line of the table, which is 300 Kelvin, is highlighted in blue. We can read off the values of specific volume for saturated liquid, subscript F, and saturated vapor, subscript G, at 300 Kelvin. Now we need to compare our actual specific volume to the specific volume of the saturated liquid and saturated vapor. What we find is that our actual volume is between VF and VG. So this means that the CO2 is a vapor-liquid mixture, because its properties are between the properties of vapor and the properties of liquid. That means that we will be using values from the saturation table. So the next step is that we need to actually find the value of the quality for this mixture. And remember, we get specific volume by doing a weighted average of VG and VF. We can take the first equation on this page and rearrange it to solve for quality X. If we do that, we can then plug in our values for the actual V, VF, and VG, and we can solve for quality, and we find that the quality is equal to 0.235. Then, the next step is to use that value of quality to get an appropriate weighted average of internal energy values. So we want to get U in terms of UG, and UF. Okay, so going back to the saturated CO2 table, we look at the line for 300 Kelvin and look up the values for UF and UG, the ones that are highlighted in yellow. Then we can plug numbers into the weighted average and find a value for specific internal energy. So summarizing the answers to question 2, if we have CO2 at 300 Kelvin with specific volume equal to 0.002 meters cubed per kilogram, we find that it is a two-phase mixture of saturated liquid and vapor. It has a quality equal to 0.235, and its specific internal energy is equal to 294.33 kilojoules per kilogram. Let's go on to the last question of this presentation. In this problem, CO2 is at 270 Kelvin and has a specific volume equal to 0.047288 meters cubed per kilogram. We want to find what phase is present, and we want to find the values of pressure and specific entropy. As in question 2, we don't actually know the phase at the start of the problem, but also as in question 2, we want to start out with visiting the saturation table so that we can compare our actual values to saturated liquid and vapor values. So I've highlighted in blue the line corresponding to a temperature of 270 Kelvin. And on that line, we can read off VF and VG. Now, as before, we want to compare our actual value of V to VF and VG. In this case, our actual V is greater than VG and, of course, much greater than VF. This means that CO2 is not saturated. Because V is greater than VG, we know that it's actually a superheated vapor because superheated vapors are less dense than saturated vapors. That means we need to go to a superheated vapor table. This time, the format of the data does not work all that well with the information that we have. The superheated vapor table is made up of smaller tables, each corresponding to a different value of pressure. Unfortunately, though, we don't know the value of pressure for our system. So, we just need to look through the different subtables corresponding to different pressures. In each table, we look at the line corresponding to the known specified temperature, 270 Kelvin, and we compare the table's value of specific volume to the actual value. Fortunately, the table for 1 megapascal has a value of V at 270 Kelvin that agrees with our known value. So we can conclude that the CO2 in problem 3 is at 1 megapascal and 270 Kelvin. So then, the last step is to read the specific entropy off of that line of the 1 megapascal subtable. And here we summarize the answers to question 3. So if we have CO2 at 270 Kelvin with a specific volume of 0.047288, then it is a superheated vapor, its pressure is 1 megapascal, and its specific entropy is 2.192 joules per gram Kelvin. Now, if you'd like to check whether you can apply these methods yourself, you can do these 3 problems on your own. If you want to solve them, pause the video, write down the problems, and then scroll back through the video to find the numbers that you need from the tables that we've already used. When you're done, you can go to the last part of the video to see the answers. And here are the answers. Thank you.